Today I'm going to show you how to do some cool stuff in GLSL and pops. In particular, I'm going to be showing you how to make a vector field that points individual sticks at the north and south poles of a magnet. And those magnets can move through space. They are modular objects. We can change their movement, make them go a bit faster, a bit slower. We can change things like the scale of our little lines, as well as the strength that this magnetic field has. So it can be turning greatly in accordance to how far away it is from the magnet, or it can be turning not very much. So yeah, there's a lot of cool things that I learned while doing this, and I borrowed the implementation from shadertoy, so I'll be sharing that next. So the part of the shader implementation that I'm borrowing is from Gijs Bellard, a Dutch shader programmer. And essentially, he's created a sketch where each of these sticks is their own magnet with a north and south pole, and they're facing these larger magnets based on their polarity. So here you can see that all of the individual norths are facing our south pole, and all of our souths are facing our north pole, and depending on the orientation of my magnet, you can see these sort of big swirly patterns start to emerge. And this is currently with a constant magnetic force being applied on all of them, but we can actually change that. And we can also make this happen not only with a grid of points, but with a moving series of points, either with some noise or some randomization. Cool. So to begin, I'm going to get rid of everything. So I'm going to take everything, I'm going to right click, I'm going to collapse selected, so it's in this node if I need it for reference. And I'm going to start by making a field of points. In particular, I want to go for a point generator, and I personally want it to be on a rectangle, one by one, and I don't want 1,000 points. Let's say for now, I don't want 10,000, let's just say for now I want 2,000 points. Oops. 2,000 points randomly distributed on a rectangle in a square. Cool. So next, I'm just going to make the points of reference the actual north and south poles of my magnet. I'm sure there's many better ways to do this, and I've experimented with having it as an alternate entrance into the pot. But just for convenience, I'm going to make a bunch of individual one-dimensional channels with a noise chop. So now I have a time slice, and I can make x1, x2, x1, y1, x2, y2. And great, these are 4 random values that will construct our x and y positions for my points. So I'm going to also animate them by multiplying or adding the current time step to their position. So we're constantly scrolling through this noise. Great, so we have some constantly changing noise, and we are actually just going to bring this right into a GLSL pod. And I'm going to go ahead and render this directly so that we don't have to do the render setup later. You take it out to a geo, camera, render, and a line. And this line for now I'm going to have with both, I'm going to drop it onto my geo as a material. And I'm going to give it both points and lines for now because we're going to be adding in lines later with the copy pop. And I'm just going to zoom in on this and throw it up in my background. So great, we're looking at an evenly distributed field of points on a black background. And what we're going to do for now is we are going to make our points of reference also visualized in a geo. I'm going to get a line pop, and I'm just going to use these same points over here for point 1, x and y, and point 2, x and y. And in particular, I don't want any divisions, and I'm going to go out to another geo, and it should be in the same world space. So I'll create another line. Great, so here's our line with these randomly moving points. They're not moving that much, probably because they need a bigger amplitude, maybe an offset, and also let's turn offline, turn on points, make these points way bigger. So we have our points of reference in our scene. And just so it looks a little nicer, I'll make it 1280 as well. Zoom in. Great. So now I'm going to go into my GLSL pop and I'm going to start constructing the parts of this that actually tell each of these how to move. So what we're doing is we're going to give all of these points a new set of normals depending on their relationship to either the positive point or the negative point. So to do this, I'm going to define my positive and negative points in my GLSL. I'm going to start in my code where I'm going to write a uniform, where I'm going to write two uniforms, a uniform vec2, so a position on x and y, called upos. And this might get confusing with position, so I'm actually going to call it plus for plus sign. And then a uniform vec2, u min for minus sign, not with a capital. Right, and now we need to add these vectors into our GLSL pop over here because they don't currently exist. It's searching. Oops, it's searching for the name of these, but there are no vectors in my GLSL. So I'm going to have it look at u plus, which is going to be a vector, a vec2, which I'm going to reference my first x1, y1. Great. So now u plus is the location that I set in noise here. And I'm going to do the same exact thing for u min. It's going to be a vec2 looking at those x2, y2 points. Great, so the shader's now aware of those two positions without having to bring it in as a separate pop. We can do that, it would just take a little bit different code. And what I'm going to do is I'm also going to add a global strength. So how much should these sticks be turning based on their polarity and closeness to our other points? So I'm going to make a uniform float. And this is going to be a constant number scale. Great. And I can add that here. Actually, I'll make that U scale for uniform scale. And I'll call that 0.5 for now. Cool, so we can actually start writing a new normal position. So to do that, I'm going to go to GLSL, output attributes n. And I'm now going to write into the shader memory, vec2 pos is equal to td in on the position, and we're only looking at xy. We're not looking at the z, because this is all happening in 3 dimensions with the z value, but we're not paying attention to that right now. Maybe I'll update this with a 3rd dimension in the future. But now we are going to make all of the vectors of these point towards our poles. So I'm going to go to vectors, I'm going to go to n, so we can see all of our vectors are pointed one direction right now. And then we're going to, from our position, make a new vec2 that essentially points directly at our plus and minus. So we're going to make 2 new vectors, one vector that points at the positive position and one that points at the negative. So we're going to do a vec2, and we're going to call that delta 1, and that's equal to u plus minus pos. So for each point, it's going to look at a new vector, a new direction, that points directly at u plus. And what we're going to do is also mirror that on the min. So we're going to do a vec2 delta 2 is equal to u min minus pos. And from there, we're going to calculate our distances. So what we haven't done now is we have a general direction that these are facing, but we don't have a distance for each of these directions or a length of these arrows. And right now we can't see these new vectors because they only exist in our shader space. if I wanted to expose these new vectors for each point, I'd have to output a separate value. Like instead of n, it would be like, all right, I'll put delta 1 as a new attribute to look at for each point. So to get these strengths or distances, we're going to create two floats for these as well. So for every direction that we face, we're going to get a corresponding distance or strength. So it's going to be a float d1 is equal to the dot product of delta 1 by itself. So what this essentially does is it creates a squared distance for us, not the square root of or length that we then have to multiply, that we then would have to multiply by itself, but the dot product essentially gives us the distance from any one of these points to a point of interest, like our positive pole or our negative pole. And we're going to be doing that on itself. And we're also going to be clamping this value at something very low and close to 0. So to do this, we're going to use the max function to get the maximum out of two values. And this is essentially going to make it so that this value cannot reach 0, because if a point in our field eclipses or goes over a point like our poles, we would divide by 0. So we're going to avoid that by clamping it to 1e minus 6. So that's 0.1 with 6 zeros before it. We're going to add a semicolon, and we're going to repeat this for d2. And then we're going to clamp it. Great. And now we're going to calculate our forces based off of this. So now that we have the distances and now that we have the directions, we're going to combine this to be a positive force that makes it point towards north, and a repelling force, which pushes it away from south. So away from our minus value. So to do this, I'm going to create a vec2. That's our force, so F1. And it's going to be delta 1 divided by d1. And that should give us an error. Okay, cool. So we have to finish that out. Great. So this is going to essentially make all of those vectors that were of the same exact length, but pointing at the same place, variably longer or shorter based off of their proximity to the point. And then we're going to do the same for F2, or force 2, where we're going to compute the negative. So we're going to compute the exact opposite direction that it has to be facing for minus. So for delta 2, we're going to divide by d2. Great, and the last thing that we have to do is we have to add these forces together and normalize them. And then we can use the strength that we defined before to determine, okay, are you going to do 2 rotations, 3 rotations when a point moves nearby you? Are you going to just, just how much this force is actually affecting your direction? So to do that, we're going to create a vec2, and that's going to be called field. It's going to be equal to the normalize of F1 plus F2. Oops. And then we can multiply by U scale. And that should give us, okay, and now we actually have to output the actual normal value. So to do that, we're going to say normal value, or that normal attribute, should be placed in order and should be equal to a vec3 that is comprised of a vec2 float and then a third value, which is 0. So field, actually, not float. So it's going to be field plus float. So this is a vec3, it's comprised of 3 numbers. And we should not have an error. Vec3 constructor, too many arguments. Maybe I can just say, maybe I can cast this. Oh, not 0, comma 0, 0.0. Great, so now we should be getting these normal values out, and we can see that they've changed over here. And this is cool, a cool visualization. I actually haven't seen it with the attribute arrows before. But we can actually use copy to make this a piece of geometry so we can see it in our render. And then we might have to do some math in between. So here, I'm going to do a math, and I'm going to make a copy as well. We're going to put this into the second input of our copy, so it's going to be the indices at which we place things like points and lines. So I'm going to make a line, and I'm going to make it be at, cool, so I'm going to make it a straight line going up, so 0, 0, 0, 0, 1, 0, and I'm just going to make this a bit smaller, so I'm going to say negative 0.1 on point 0 and 0.1 here. So it's a straight line going up with 0, 0, 0 at its midsection, and it's very short. And we're going to take line and we're going to bring it into copy, and we should see none of the rotations are applied because we have to go to template, and we actually have to rotate each of these by an attribute, which is going to be our normal. Now you might see some very slight wiggling, but this is because when we did our normalize, we made those values go between 0 and 1, as they usually are between 0 and 1 for normals. And then we have to essentially rescale this from 0 to 1 back to degrees, or 0 to 360. So I just go into my math, and in my map to high, I'm going to put 360. I actually messed up in my math, I didn't say that I wanted to only affect my normal values. So I can bring this way back down. Cool, so these are much more reasonable sizes. Great, so this is our flow field, our vector flow field. I made the thickness a bit larger, but we can see in our line we can make the thickness whatever we want. And we can see now that when a point gets close to somewhere on the field, the north side of the line attracts to it, and the inverse happens when the other pole gets close to it. So they flip directions depending on what pole they're closest to. And we can get some of these really fun swirly patterns out of it. You can change a lot about this setup as it is. So you can change the shape that you're copying. You can change the sort of global scale, how much every single line is rotating. So if you have it scale be very low, it's just going to do a slight wiggle towards the line or a slight attraction. And now I've actually changed my line so that it's not, so negative 0.05. So now they're all right on, like their fulcrum is in their middle. And that can change a lot. I can change the number of points modularly. I can change the C to my randomness. I'm going to bring the scale back up. I think, yeah, with this length, maybe I'll just scale it down. We can also do things like changing the scale based off this rotation. So here, before we do the math, we know for a fact that anything turning a lot gets a value closer to 1, and anything not turning a lot, or not having its direction change much, is going to be closer to 0. So what we can do is we can say, use math mix into our math, and my math mix is just going to look at a value A and assign it to another value. So I'm going to look at N, and I'm going to assign it another attribute name of S. And I can say, hey, point scale, just look at S. And so now the lines appear bigger if they are turning more. Kind of disappear if they're not being affected much by that field. Yeah, and you can also do a lot just with your points in general. This code currently only works with 2 points. This is a dipole setup, but you can change this with other types of magnet systems. These are the kinds of patterns that arise when you put magnets on ferrous sand. And yeah, I think you can totally have fun with it. You can even now use the ends of those points that are moving, because we should have made sure in line that our divisions are low, so it's just 2 points for each of them with a line connecting them. And it's kind of cool to just throw in a trail. And so now we get more of circles filling themselves out depending on how close these guys are. Yeah, so you can also, oh, that actually crashes my CPU or my GPU. Yeah, we can also change, yeah, this starting geometry even. So if instead I wanted just a grid, I could throw that in there as well, and it would happen on a grid and not be so random starting positions. So I can update that, however. And since this is not in a feedback loop, anything that happens before a GLSL gets applied directly. If you want these sort of to be building off of the last frame or to have these positions be in a feedback loop, adding a feedback loop doesn't affect anything with how this works. So yeah, that's it. I hope you have a lot of fun with this.